All right, Dr. Grow. I'll start off with the model that we created for our hand. So here it is. As you can see, it's a kind of realistic looking prosthetic, 5 fingers. So the way our finger works, if we go ahead and take a sectional view of this, as you can see, mounted inside of the palm, we have a DC motor which is connected to a gearbox and then to a screwdriver. This DC motor is mounted with a bracket to a pin in the back so that it's able to rotate up and down, which it'll need to do as it's moving. As the screwdriver turns, this collar will extend in and out based off of the direction. This collar extending in and out will push this member connected to our finger, which will then cause the finger to rotate about this joint, and this member will come down. As this member comes down, we have a linkage that connects this point to this point on the end of the finger, and that will push this around this rotational axis, which will then cause this end of the finger to rotate and cause the finger to pull in, which can be seen here. So screwdriver goes out, collar screws in one direction, the collar will move out, pushing all of the finger and everything, and then it goes in reverse and it pulls this back in. So that's our theoretical. Prototype 1, we have just the finger. Right here we have a pseudo knuckle, so pretty much this just like simulates the knuckle as it would be, coming out of the palm. Pretty much you hold that here, and we pull this piece down, and we get bending of the finger. So moving on from this prototype, we have the prototype for our hand. So you can see right now we just have 2 fingers attached, thumb and pointer finger. As you can see, this is kind of what it would look like with the collar or the little collar attached to the motor. This would extend out and this would bend. We have a demo for this movement in one of our other videos. Popping off the front of our palm, you can see how this motor is mounted inside as is shown in the model. This is able to rotate, this moves out, and finger would come down. Again, this is shown in one of our, the motion is shown in one of our videos.
These are the kinematic, inverse kinematic, and velocity equations for our fingers. The finger, as you can see here, was split into 2 different systems. We have a PR, and then we have an RR for 2 separate systems respectively. We're treating our motor as a linear actuator in terms of kinematics, which the length of this linear actuator will be represented with delta. And then the angle F1 is used for the angle of our member right here. With that, we can create our kinematic equations and then our inverse kinematic equations, which we will solve for F1, which is for theta 1, and for delta. Moving on to the second part of our finger, we take the coordinates x1 and y1 from our from the first part of our system, and we add it onto the origin for this system. We have more angles now. We have theta 2 and theta 3, and we have length 1 and length 2, which is represented by a straight dotted line despite having curvature in the finger. With that, we can make some basic kinematic equations, add x1 and y1 from our last system onto this to have a better representation of where our finger is at on a axis, and then we can develop some inverse kinetic equations from our kinematic equations, solving for theta 3 and theta 2.
Okay, moving back to the hand. Oh, and I should actually mention this as well. On this actual hand right here, we have this little part right here. This is where we'd connect a stepper motor to for the wrist action. So pretty much stepper motor through a collet. You just connect it right here and rotate about this. As far as sensors in the hand, one type of sensor that we're going to use is a linear potentiometer. This will be connected on the bottom of our motor here, and then we'll have a little linkage that'll connect this fin to the collar here, and pretty much as this moves up and down, so will this, and via that we can tell how much this part has moved in and out, and thus how curled the finger is, because the further out this is, the more curled the finger will be, and the further in it is, the more straight the finger will be. The other type of sensor that we intend to use is a pressure sensor. So we'll kind of, on one of the fingers, we'll have it connected kind of like to the tip of the finger, and it'll kind of be connected through here and run some wires down through here. And the way this will pretty much work is resistance of it changes as you apply pressure to it. So as soon as this comes into contact with a device, we'll be able to read the change in resistance, or well, change in voltage due to change in resistance, and thus we can detect a pressure. So we'll actually know when our finger has come into contact with something. Further stuff, or further improvements we're going to make to this. Obviously, 3D printed plastic is, plastic. It's a little slippery and whatnot, kind of hard to grip things. So our plan there is to use a product that's called Plastidip. Pretty much, it's something if you had like some like pliers that didn't have like a plastic grip on the handle, you would dip this in that and then pull it out, and then it would dry, and you'd have a nice grippy plastic surface. There's a clear version of this product, and we're going to dip the ends of these fingers in that, and it'll leave a nice, clear, rubbery surface on this, which will increase the grip of our fingers, and thus make it easier to grip the washer and the ping pong balls.